So today we're going to talk about vector fields. First of all, let me talk about vector in the XY plane. Okay. So how do we describe vector? They describe vector in two different ways. One is you need 2 points, then you have an error. That's called a vector. Okay. Now it have coordinates P and R. That's P and Q, and here let's use a coordinate x1, y1, and here x2, y2. So a vector actually is determined by 2 sets of coordinates, okay, by 2 points from P and Q. So P and Q is described in this notation. So it tells you precise location of the vector and the length of the vector. Okay, but the vector, sometimes you don't care where it is located. Okay, and if you already know the starting point, then the vector can be also described by the following notation. This is the vector can be also described using just one pair of numbers. Okay, so this can be sometimes it can be also described by another notation that's called A. Okay, so this can be this is going to be x2 minus x1, y2 minus y1. So this notation means a vector. It's starting from, it's hard, if you really want to draw it, then you have to draw a family of them because different if you move this vector around in the space parallelly, and the difference will be not changed. x2 minus x1, y2 minus y1 will be the same. Okay. For example, if you move it to here, as long as you don't change the length, then as long as it's parallel to the original one, then the difference of the coordinates, okay, will give you the same, that will be same. It will remain unchanged. So well, it depends. For the computation purpose, we denote the vector by this notation. By this notation, it's called angle, something like that. Okay. So it can be described not by pair of numbers, but not even they're not one-to-one correspondence. Okay, so given P and Q and the direct orientation from P to Q, then you get A. But conversely, given A, then you have a bunch of vectors all over the space, unless you already know where the starting point. Clear? Okay. So that's the way, this is that's 2 different ways to describe a vector. Okay. Now we're talking about vector field. Okay. Vector fields on R2. Vector fields on 2 is just a family of vectors at a given point over space. So first of all, let's draw it. Let's draw it. So those are called the vector. If at every point you have a vector, okay, then this is called the vector fields. A vector field, roughly speaking, is this actually can be also viewed as a function. Suppose a vector field on D. Okay, this actually assign to each point a vector. Okay, so the vector field is actually a function that assigns to each point a vector. Okay, so it's just a family of vectors. Okay, and over this domain D, at every point there's one vector there attached to this. Okay, it's like a, yeah. So this is this is called a vector. So here's give precise definition. It is a function, capital F, okay, that assigns to each point x and y, let's call it, in V a two-dimensional vector f x y. Okay, so usually f x y is written in the following form. Okay, this could be the first coordinate as a function of x and y. The second coordinate is a function of y. Okay. Yeah. So a two-dimensional vector. Okay. So the if you want to draw that vector, you see, given this notation, you have a, you know, if you give it two numbers a and b, I just said that you have a, you know, you have vectors over the plane, but since we are you know, since it's clear that the starting point is at x and y, so actually when you draw the vector, you have a starting point and you have the direction. Okay, so so it can be uniquely determined. So this is a point, x and y, and then here's a vector. Okay, so the vector, so it's not at the end, so the vector is denoted by this notation. Okay, so if you want to find the coordinates of the tip of this point, you have to add a to x, b to y. Okay, because that's the starting point, and the f is just tells you the the first coordinate, just the difference of the first coordinates of those 2 points. Okay. So we can describe f of y in the following form, and this can be a x y, and this is I and b x y and j. So I is going to be the vector 0 1 was coordinate 0 1, j is going to be 0 and 1. Okay, that's another notation. And similarly, you can define vector field in a 3-dimensional space. Just use a you just use 3 variables, and you have 3 components. Okay, as long as you understand the 2-dimensional case, then you can understand the 3-dimensional case. But now, the difficult part is to draw to draw the vector field in the given region. Okay, so here here let's look at the example. Okay, a vector field on R2 is defined by, okay, so we're going to put x and y here, just like this. Okay, simple. Okay, so we have to describe it. What's the question? Describe f by sketch some of the vectors. Okay, sketch it. It's called sketch. Sketch the vector field. When you sketch it, you just need to draw, pick up a few points, then and draw the vector at each point. Okay, so this is a picture. X and Y, okay? Take an arbitrary point. Let's just look at an arbitrary point, okay? And at this point, okay? At this point, F AB is just A and B, right? So what does that mean? Okay, so this is a vector. Okay, first of all, this is not the really tangent vector. Okay, so this just let me see. Yeah, I put it. Yeah. So if you want to just draw the vector was called coordinates A and B, and you just, if you don't know where's the starting point, you just draw from the vertex from the origin, okay, and to the point was coordinates A and B, okay. Since we already know this is a vector field, okay, defined on the space, and so in that case, you already know the starting point. So this should be, you have to move that vector parallel to here, okay, and keep the same length, okay. So that is a vector you have to draw, okay, for the given vector field, because it's already, it says that at x, y, the point x, y, and those, you get a vector with components x and y, okay. If you don't know as a starting point, and you just draw one from the origin to that point with coordinates A and B. But I already know that, so you have to draw the stuff start from there. Then the point, if it's further away, then this vector is getting longer. Direction will be not changed. So what you can get here is, like that, okay? And then if you draw the circle around that, and then around this circle, the lengths are all the same. You should draw the same. You should draw vectors with the same length. Okay, and then when it's getting close to this origin, then the vector is getting shorter. Okay. Right. So got idea. So this is enough to tell how the vector field looks like. It's starting from the origin, okay? The vector at the origin is 0, no direction, and then gradually the length is getting longer, but they're all in the same direction, okay? Yeah, they're, along each line from the origin, the vectors will be in the same direction, just getting longer if it's getting far away from the origin, okay? So this is a good picture. So you sketch graph, that's enough. Okay. Another question is, let's say sketch the vector field f, x, and y. This time I'm going to only use 1 and 1. Okay. So that means the first component is always equal 1. The second component is 1. Right. We find out where this disconnect.
Oh,
yeah. No, we find out it's here, hidden here. It's plugging.
Oh, okay.
Somebody pulled out accident.
All right.
I'm sorry.
Oh, no problem.
Yeah. All right. So sketch the vector field in the XY plane. So you have to pick up a bunch of points. Okay. Of course, you can make a table to do the computation if you want, but if you can do the computation when you draw it by mind, that's great. Okay. Sometimes it's easy to see. So you get a bunch of points. What you should do is at least, those are the important points. You can 1, 2, 3, 4, 5, right? Total, those are the points. At those points you have to draw the vector. Okay. Use a different color. So when x equals 0, when x equals 1, y 0. When x equals 1, y 0, the corresponding vector will be 1, 0, 1, 0. 1, 0 is going to be that direction. Okay? And when x equals, at that point, when x equals 1, y equals 1, it's going to be 1, 1. So that be in that direction. Okay? Then here, at that point, 1, negative 1, y is going to be negative. So it's going to be that direction. Okay? But then you look at this point, when x equals 0, y, y is 1. So it's the same, parallel to that one. Okay? Because the first component is always equal. And here it's the same story here. The first component, if it's 1, negative 1 and 1, then the corresponding vector will be always have components 1 and 1. So you have 3 vectors parallel to each other, same length. Okay? And the same here, along every horizontal line, all the vectors will be the same. Okay? And along, if we draw the one already, then you can draw the 3 along each horizontal line. Because along the horizontal line, the x component changes of the point. But when you look at the corresponding vector, the first component is independent of x. So that's why only the second component, which is determined by horizontal. So this is a picture. You can draw the graph like that. Okay. I can. Of course, the length of those vectors changes. Okay, when the point is going high and high, and the vector is getting more and more vertical, because the y variable is increasing. Okay, imagine. So if I go down here, the vector will be looks like that, and even longer. Okay, it's not the same length. Yeah, so it's going to be like this, much longer. Okay. Yeah. Why? The length. How do you calculate the length? The length is going to be the square of 1 minus square of 1 square plus y square. Okay, that is the length of the vector. Okay, the components here is 0 and the y. Okay, yeah, 0 and y, and the corresponding vector, okay, is going to be 1 and the y. Okay, so the length is the square of 1 square plus y square. If you are only given this notation, okay, and this is a notation for the vector, then how do you draw it? You don't know where the starting point, you always put in the denominator. The starting point is always the origin. But if you know the location, then you can draw the vector more precisely if you know the starting point. Okay? Yeah, another interesting problem is sketch the vector field f x y. There's that difference. First of all, you can get negative y and x. Okay, negative y and x. First of all, you should know that those two vectors are perpendicular to each other. Okay, and if you want to draw it, if this is the origin, if this is a and the b starting point, then negative b and a will be here. Okay, we should know that. And they're perpendicular to each other. Okay, So those two vectors are perpendicular because the inner product is going to be 0. Remember, if this is the angle theta, then the inner product is going to be negative b times a plus a times b, which is going to be 0. But this is also equal to, remember, is going to be the length of the first vector and the length of the second vector and times cosine theta. So cosine theta is 0, theta must be 90 degrees. Okay? So this implies theta is going to be 90 degrees. Okay? All right, so once you see that, then we can draw the graph. Okay? I'm going to draw the graph around the circles larger than gradually increased. Okay? The reason I want to do that because along each circle, the length of the vector is always fixed. Okay, along each circle. Okay, so here, so this is a point x and y, right? This is with a vector. Okay, so the real vector in red color will be perpendicular to this one, will be the same length, but in that direction. Okay, so this is the vector f. Okay, so now you rotate along the circle, have the same length. They're all perpendicular to the so-called radian vector. Perpendicular. This is at 90 degree. 90 degree. Okay. Then if the circle is smaller, then the vector is shorter. That's it. But they're all tangent to the circle. Okay. So you can see that this is a special vector field, and it's rotating around the center, but it's getting longer and longer when it's getting away. How long it is, or which vector? It really is the length of the vector will be the distance between the point and its origin. Okay, so the length of this vector is going to be, right? It is going to be negative y squared plus x squared, which is the same as x squared plus y squared. It is going to be the distance between the origin and the point, the foot point of the vector. Okay, so you can imagine the vector field is getting longer when far getting away from the origin. Okay. Yeah, sometimes you just like draw the function, draw the graph of function. Sometimes you have to choose a special point and then calculate the values. Okay, and then you plug draw the vector at each point you selected. Okay. Okay. Now, if I modify the problem, sketch the vector field. Let's assume all right, what does that mean? So I is just the inner product, so it can be written in the following form. Okay. First of all, you notice that this is a unit vector at every point. The first point, the length of this vector is always equal 1 at every point. Second, undefined at its origin, because when it's origin, the denominator is 0. Okay, so this is a vector field. It's defined away from the origin. And if you want to draw, it's always, yeah. So the direction, the third one, the direction is the same as the vector from the origin to that point. Okay. The direction of F is the same as, okay, as a vector from the origin to the point x and y, okay? Because proportional to this. So if you draw the graph, no matter where you put it, this is the direction, but there's constant length, okay? So you're not going to get longer vector. So when you draw it, be careful. If you draw it here, it's still the same length, okay? Okay. So you just add more. Yeah, this is the way we draw it. Okay. So when you look at this picture, okay, it's just going out, but the vector has constant length. Okay, with the same length. One. They're all unit vectors. They're all unit vectors. It's going out. Okay. They're all unit vectors. Okay, so this is how they draw. So you catch the key points of the vector, the key properties of the vector. And then you can start to draw it. Okay, you can only draw a few of them, but you make sure you understand the vector. You make sure the length, how does the length changes. It's also important, and the direction. Now, we define the vector field in three-dimensional space in a similar way, but it's a little bit more complicated three-dimensional space. It's harder to draw it actually. Okay, so let's sketch the graph. Sketch the vector field f x y z. It's given by z and I. It's in three-dimensional space. Okay. So you will see that the length of f at the point x, y, z depends on certain component. If we're getting high and high, then the length is again, this first component, it's x, y, and z. But it's harder to draw it. Okay. But we see that the value of, so first of all those vectors, I think parallel to the x-axis. Okay, so you have to write down a few points. So f is parallel to the x-axis. Okay. Second, the length depends on how high of the point. The length, right, is going to be z, absolute value z. So if z at the origin, then it's nothing there along this. Okay, let's just draw the vector field in the xz plane. In the xz plane, when it's getting high, then those are the constant vectors, right? Yeah, they're parallel to the x-axis. and it's even getting longer. Yeah, the length is getting longer when it's getting high, right? And then once it's clear, you can draw at a different location. It's really independent y, right? So a different location here, it's going to be 0. You cannot draw the vector, okay? But you have to in the space here. Yeah, this is above the ground, right? Above the XY plane, you know, one unit above. Then it's getting high, then you have to draw longer vector field. Yeah. So maybe I should use a different colors. Yeah, right. So now I only draw 2 layers of vectors, but to give a pretty good idea how does it look like. Okay, and now it's getting high and it's getting longer. Okay, along this line. This is the line perpendicular to y-axis. So I have 2 layers. Imagine I have 2 planes perpendicular to y-axis. Okay, and on these 2 parallel planes, the vector fields look same. Okay, when they are getting close to the XY plane, the length is getting shorter and shorter because it depends on z value. Okay, it depends on z value. Okay, so when it's getting high and high, and then it's getting longer. Now, if it's below the XY plane, and somewhere here is going to the other direction, so it switch the orientation, the direction of the vector field across the XY plane, right? Yeah. So above the XY plane, they all point to the positive x-axis. Below the XY plane, all the vectors pointed to the opposite direction, negative direction of the x-axis. Okay, so if you can describe it clearly like that, then you get, yeah, correct the picture. So this is a longer because the z value is negatively large. Okay, and here along the XY plane, the vectors are all equal or 0, degenerate. Okay, so imagine you're going across the XY plane. Okay, you change the vectors. The vectors are getting shorter and shorter. The direction will not change. Then after if you go across the XY plane, then the vector is getting longer and longer, but then change the orientation. Okay, so this is a little bit difficult to draw. It's 3-dimensional. Now, given the function in the given a function f defined on a D in R2, okay? So f is a function of x0, that's just function, right? So this is the domain D, the function defined that. We find out at every point x and y, I can get the vector. This is called the gradient. Oops. Okay, this is called the gradient. And how do we understand this? so the gradient is going to be, yeah, at each point, x and y in D, okay? There's a vector associated with that. The so-called gradient of f at x, y is going to be defined to be f x, y partial derivative. Okay, so it gives you the vector. Now, what's the meaning of this? This is going to be the notation. Yeah, it's called nabla. Okay, so this is called nabla. Nabla of f. Yeah, pronounced as nabla. So the gradient of function f at the point is a vector. So now you get a vector field over the space. Now, what is the geometric meaning of this vector? As a geometric meaning of this vector, remember, you can have a level curve, right? That the gradient is a vector perpendicular to the level curve. Okay, how do you see that? And it also tells you how fast. If it's longer, then means the level curve, the level, the value of k changes quickly. Okay. Yeah, the length of the gradient tells you how fast the level, if you go down the hill, right? The level curve tells you how height of the mountain along this line, along this curve, okay? Now then, actually, at every point, there is a gradient vector field, okay? You can find out based on the height function, okay? If the gradient is longer, it means it changes the height quick when you're going down the hill, okay? So why is it perpendicular? The proof is very simple. So we parameterize the level curve by x over t, y over t, right? Yeah, this is a parameterization for the level curve. So that means it's always constant, okay? If it's always constant, then you differentiate with respect to t. When you differentiate with respect to t, you get, right? You get 0. So this is really the gradient of f and the inner product. This is going to be 0. Okay, so that means the gradient is perpendicular. This is a tangent vector to the level curve, right? And this is a gradient. So the gradient is perpendicular to the tangent vector to the level curve. Then, in other words, the gradient of the function at that particular point is perpendicular to the level curve. Okay, so this is the reason is perpendicular to the level curve at that particular point. Right, so that's the geometry meaning of the level gradient. Gradient. Okay, so let's take a look at some questions. All right. So, given the function square root of x squared plus y squared. Find the gradient of this function. Now, before we solve the problem, let's see what we can get. So level curve, how does the level curve look like? The level curve f of x, y equals r, positive. Let's use a positive value. F of x, y equals r means square root x squared plus y squared equals r. So that means x squared plus y squared equals r squared. That's the equation for the circle. So the level curves of the circle was the radius r. Okay? The circle, level curve, f equals r. Okay? And so the gradient must be perpendicular to the circle. Okay? So perpendicular to the circle means it's multiple of the vector. So before I solve the problem, the gradient of f must be at every point is going to be a multiple of the vector from the origin to that particular point. Okay? It must be in that form before you do the calculation. Because it's perpendicular to the circle, then this must be parallel to the vector from the origin to that point. Okay, if that point is x and y, then that vector will be in this notation. That's slightly different. Okay, then this is my gradient. That should be a multiple of this. All right, so let's compute it directly. Okay, fx partial derivative, right? And this is going to be x squared plus y squared to the 1/2. So when you differentiate, you get the 1/2 x squared plus y squared negative 1/2 and a 2x. Right? So after simplified, you get this. And similarly, fy is going to be y over of this. All right? So now the gradient is going to be x over this, y over that, right? So this is the same square root. You can take it out. And that's what we predict at the very beginning. It's a multiple of the vector. Okay? And it actually, in this particular case, the length is unit. This is the length of this gradient is always equal 1. Right? It's always equal 1. You can easily to see that squared. So if you want to sketch the gradient of the function as a vector field, you know how to sketch it. It's multiple, right? They have the same, we already did that, right? It has the same length. So it's going to be like that. And it's always a unit. Right. So this is a gradient of the function. Okay. What? It's connecting. Okay. All right. So so now let's look at the next problem. F of x, y is going to be x squared, x, y, z. It's 3 variable, okay? X, y, z, and the e to the y over z. Now this is a a function defined as 3-dimensional space. This is a function defined 3-dimensional space. And what's the meaning of the gradient? The gradient is going to be vector field in 3-dimensional space. The geometric meaning of this is suppose, so suppose this is a domain D, okay? Region, let's call it R, 3-dimensional. Okay. And this web is a level surface. Okay. The level surface. So the gradient is going to be at a point x, y, z. This web is a gradient. It is perpendicular. The gradient must be perpendicular to the level surface. The same idea to prove. So the important fact is the gradient of the function perpendicular to the level surface, okay, at every point. Okay, so let's compute it. So f is x squared, y is, it's hard to draw the graph, okay, because the function is complicated. It's hard to draw the level surface. But we can, let me write down again the function. We can find the gradient, x, y. Okay, so first of all, you have to find the partial derivative with respect to x. It's going to be 2xy e to the y over z. And f sub y, it's a little bit more complicated. First of all, you use a product rule. Then the derivative of e to the x y z, and that is going to be 1 over z, okay? E to the y over z. Then fz is going to be x squared y e to the y over z. When you differentiate of this y over z, you get y over negative y over z squared. So that's it. So the gradient is very complicated function. Okay. Yeah, but you have to say that the gradient is going to be, if you don't want to copy, let's write down the formula. So 2xy e to the y over z, and this will be x squared e to the y over z plus x squared y over z e to the y over z. Then the third component, here's z squared, here's y squared e to the y over z. Yeah, it's very complicated. Okay, it's hard to draw it. So you're not asked to draw the graph here for this particular problem. All right, so let's look at an easy one. So we have xy. That will be the 2-dimensional case. Okay, let's try this. Find the gradient of xy and sketch it. two-dimensional, yeah, it's easier to handle. Right, so the gradient, the partial derivative, the first one will be just x. This is going to be 0. Okay. So the gradient is going to be x and 0. Okay, let's draw the graph. How do you do that? The second so this is the first component. The second component is always 0. So this vector is always horizontal. Right? It depends on it depends on the first component. Okay? So this is x, this is y axis. So at every point here, it's horizontal, but yeah, you draw the graph. The length is going to be the horizontal length. Okay, right? But when getting away from at this point, for example, the x is going to be 2, so it's going to be longer. And then here it's going to be short. Okay, and then short, almost 0. And here you're going to the vector is getting longer, but it's always horizontal. Nearby the y-axis, the vector fields are very short and small. Okay? But vertically, they're identical, vertically. If you draw the graph, you have to make it longer and longer, and short. Okay. So a typical example would be like this. Yes.
So why do they get longer as they go out? Like,
No,
because the vector fields are all the same length. What was the?
You don't see why it's getting longer? No, if here, this is the point x and the y, right?
Yeah.
The length is determined by, at that point, it's determined by x, right?
Okay.
Yeah, it's going to be square root of x squared plus b squared over x. So when x is getting large, then its point is away from the y-axis. Okay? Get further away from the y-axis, then the length is getting long. Okay? This goes to infinity when x goes to infinity. Okay. Now, yeah, this is an x-axis, y-axis. How does the lever curve look like? The lever curve is going to be, f of x, y equals, f of x, y equals k, right? Half of x squared equals k. So the lever curves are just the vertical lines. Okay? Now, the lever curves, when when you solve it, k cannot be negative. K must be greater than or equal to 0. Then x squared equals 2k. X is plus minus 2k. So it depends on the value. So those are the lever curves. Right? And this will be when k equals 1/2. When k equals 1/2, you get a pairs of vertical lines. Okay, so it's not a surprise the gradient is perpendicular to the level curve. Okay, another one here is when k equals 2, for example, then x is going to be plus minus 2. Okay, yeah, this is the point 2. Here's a 1. It's a 0. It's negative 1. Okay. Okay, so one more example. Find the gradient of f of x, y, and this is a y minus half of x squared, and sketch it. First of all, let's look at the level curve. The level curves looks like that. F of x or y equals k. So if you plug into here, it's going to be half of x squared plus k. So you get a bunch of parabolas. Okay, so this is the level curves. And this one when k equals 0, when k equals 1, k equals 2, right? 2, 1. Okay, and same right, and here when k equals negative 1. When you draw the family of level curves, you have to draw at least a 3. Then also have to look at whether the value of the k changes, whether the graph changes. Sometimes when k changes sign, it's completely different direction. Like a parabola, for example, the equation for the parabola. So, so you have to draw the typical curves in different for the different values of k. Okay. Otherwise, it would be take a couple points off. Okay. So I think k increases from -1 to k. So I believe that this is my gradient. That should be the same, identical. Maybe here it's longer, but along those level curves, I'm pretty sure the gradient vector fields are similar. Okay, at different location, but they're perpendicular to the parabola, right? But the vector is not going to be constant, so when you draw it, be careful with the length. Okay, so let's find out the gradient. The gradient, when you draw it, it's going to be 2, just x. Okay, so y minus, so it's going to be, x is going to be negative. And the y is always 0. It's 1. The derivative of f with respect to y is 1. So the length, thinking about the length, it's going to be square root of x squared plus 1. Okay? But still does not tell you how length of along the curve, along the parabola. if it's along the parabola, when x getting close to 0, when x getting close to 0, the length is getting close to 1, but it's always, but when x getting large, the length is getting longer, right? The vector is getting longer, the length is getting larger. So when you draw the graph, this will be the unit vector, then getting longer, longer, we get longer, okay? As long as it's getting away from the y-axis. Okay, this actually goes to positive infinity as x goes to both sides, positive infinity or negative infinity. Okay. Yeah, you find the length to help you to sketch the graph. Instead of put the vectors, identical vectors, the same length, now you change it, okay? And this vector is become more horizontal. Yeah, what is the angle between, yeah, what is the angle between the x-axis and the gradient? Okay, look at the graph, right? This is a parabola. And I'm going to, this is a vector, right? My question is, can you estimate the angle? Okay, at the particular point, x and y. Okay, so the gradient at that particular point, right, is going to be negative x and 1. So the y component is always 1. The x component is getting long, again large, right? So the vector here, this vector is going to be negative I, okay? Negative I. So this is the first phase. So negative I. Okay. So the angle cosine theta is going to be the inner product of these two. Okay. Okay. So it's going to be negative x and 1 dot product. And this is going to be x squared plus 1 has 1. So you will see that the numerator is just x plus 0. Okay. So how do you see that? It's x over square x. But this one clearly approaches 0, approaches 1, approaches 1 as x approaches positive infinity. That means theta approaches pi over 2 as x approaches positive infinity, right? No, approaches 0, no, it's pi over 2. Yeah, because cosine 0 is a 1, right? So that means when you're getting away from further away, going that direction, and the angle is getting smaller and smaller. Okay, just this can be seen from the parabola. It's because perpendicular to the tangent line to the parabola. Okay, so that's it. You know, when you draw the graph, that helps you. Helps you a lot. You know, if you know the length is getting longer, but the angle is getting smaller. Okay. So we will continue to study vectors. No, we're going to use the vector fields to do the other problem. So the next section is about line integrals. Integral along the curve, not along, yeah, integral along the curve, because sometimes we want to have to deal with not just find the length of the curve, we have to find the total mass of curve. And then you have to integrate the density function along the curve.